All right then. That says we're alive, so you all know what that means. I guess what's going on. Memes here. Yes, we're back. Yes, I know it may be a wee bit of clickbait. He's talking about the vacuum energy, but he's using the technical equation that he was using the other day. Yada yada yada. We'll all get to it. Um, all I know is I thought it was kind of pretty, and we're actually going to go through. So we're going to continue with what we were talking about. But first, a little word from our friends Fraser Kane and Dr. Gay uh, from the Astronomy Cast. Why? Because I was, oh God, of course Fraser's in the middle of doing his actual open space. Feel free to check out over there. Nobody's bound here. Feel free to go and do what you want. But so Fraser is doing that, but he's a busy man. He runs Universe Today. So Astronomy Cat. Dun, 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 dun. Okay. So we're gonna get to let me bring that up. Do they have the transcript yet? Let's see how fast YouTube works. Oh my God, they actually have the transcript up, and this was less than 8 hours ago. Okay. So let's go see. Memes. Uh, how about destruction? Uh, curvature. Oh my God. Does it not have it here? Hold on. Let's go, because they had questions at the end. Okay. Oh, well, in that case, we should probably entertain folks rather than just be scrolling through a transcript before I get there. Here, let's do this. Let's go over here.
Managed to sweep under the rug. But while Princeton had a large
and lived through what
Last time
and
the
he took
questions.
his drafts on.
Huh?
Thank you all so very much.
Here we
thanks
go.
everyone, and we will see this city that you have taken out,
Huh?
Kind of mission where you send
vibrant economy that
there.
we don't understand most culturally or becoming paid. Yeah, I guess you're as well. I wonder. Anyway, so
Yeah.
this is the kind of chaos that
Oh yeah,
we don't
yeah.
know.
Oh,
We don't know what's gonna happen.
changing regulations.
So I think for
changing business
now,
dynamics.
what things are going to be, we're here for you.
Oh wait, hold on. Is this even the one? Oh, that's why. It's see. Ah, that's why I was there. We weren't looking at the right thing. I wonder the transcript was already made. All right, that makes more sense.
It's not
Okay.
showing you the algorithm. The
Also
dystopian
the wrong
nightmare that
problem.
we live in today is that, man, it
Go
is
read
so bad
Fahrenheit
out
450.
there.
Leave me slightly confused, but the way they're looking for it is they're looking to aren't aware of.
Do we ever?
Yeah. And
Intervention for you, a way to protect.
project. I have no clue when he's going to get a chance. We're both buried in paper reviews, so hopefully, New Citizen Science coming very short.
Okay, never mind. We won't go to it.
It has
Okay, let's
decided
about the curvature of free space. Hold on. Okay, I did first. Apologies. Just complete disruption there. All right. Never mind. Never mind. We're talking about live internet here. Okay. So essentially, the question that I'd asked Dr. Pamela Gay was that I've heard that the vacuum energy is a measure of curvature of space. Is there any truth to this? And the answer that she gave, thank you again, Dr. Gay, was that basically if we interpret it as the cosmological constant, then we could view that as the curvature of space. Do we know that's what the dark energy is? No, but a number of people happen to interpret it that way. Well, to be fair, Nullius, if we are in two dimensions, it's flat. I think by definition. Yada, 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 infinitely differentiable, blah, 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 except for the Rice function, because AKA it's the wizard function. Uh, but that's a lot of stuff right there. Okay. So we've got a Snortopoopas. We've got the rare Klondike bear right there. Hopefully, I hope you're well. Things are going all right down there. Okay, I'm gonna still see if I can't find. I'm trying to find a staying clip. Hold on, I think I might have it. Uh, I'm literally hold on. Well, we got to entertain the folks. I guess. Start off with kind of guess question is always pause. Well, well. At least the court. I think the way that that Einstein had originally when he put in that whatever that this crazy thing he is. It's a Greek symbol called lambda. So basically, it means you need to adjust something. The way it's written, it's like it could be positive, it could be negative. And what we're going to get into is technically that vacuum, that dark energy. Um, is literally related to the cosmological constant. It literally is. The only difference is like 8 pi in the Planck force. So because that's the only reason I can actually try to start to interpret this at all now. Don't worry. A whole bunch of letters and some symbols and a ridiculously small number. Don't worry, that really most shouldn't really mean anything to a human being. I don't know this. But if you look at it, you're like, all right, was an interpretation of curvature of space. All right. Curves, how do we usually look at that? I don't know. It's curving around. Is there any stuff or thing within nature that relates to curviness? I mean, I like pie just because, well, it's got crust and usually tasty filling in it. Oh yeah, and there's also the constant of curvature. So we've got that 8 pi. That's the whole thing from the Einsteinian gravity. It's basically just 8 pi divided by the Planck force. Uh, so you get a really small number, and then I just use the magic of algebra, which I didn't really understand. I'm like, why does any of this matter? We're learning in like school and high school and stuff. It's like I see college and I took business math. So that's basically okay. We'll pass you along. Uh, and it's like, wait, it's just an 8 pi divided by that thingy there, that FP, because that equals the brute force. Um, you can actually break it out. And that's how we got to this dang thing. So we're gonna go through in a moment. I'm just still looking for this clip. I'm still looking. I apologize. Let's see. Yes. Hey, I mean, we learn a lot from curves. I mean, mathematicians go through and look at look at them all the time. Ah, here we go. All right, I found it. I found it. Okay. Live internet. And see, it helps when you actually do the correct live stream you're trying to find a clip from, rather than well, let's grab a link to this. So just in case if anyone wants to check this out, I'm giving credit to Fraser King because that's like the one thing. Yes, he's like, listen, you can use my content. Just just give me like a citation. Let folks know where it's coming from. Okay, so here's where we go. Share tab. Boom. All right, the vacuum energy, which I coincidentally totally name this stream because I'm an algorithmic pirate. What can I say? Here we go. Fraser, Dr. Gay, take it away.
Why I'm an observational astronomer.
Right. The memes of destruction. I've heard that vacuum energy is a measure of the curvature of space. Is there any truth of that?
If you believe that dark energy and vacuum energy are the same thing, then yes, it goes into describing the curvature of space. The two numbers don't match. However, we still haven't figured out how to quantize gravity.
I mean, that was a pretty good. That was a pretty good answer. I think it was short. It was sweet. Let's take a look at that one more time, just so I can absorb it. All right. I think.
Reminds me why I'm an observational astronomer.
Right. The memes of destruction. I've heard that vacuum energy is a measure of the curvature of space. Is there any truth of that?
If you believe that dark energy and vacuum energy are the same thing, then yes, it goes into describing the curvature of space. The two numbers don't match. However, we still haven't figured out how to quantize gravity.
Okay. I want to listen to that last part again because I'm still trying to grok. When she says they don't match, is she talking about the whole like that 8 pi over the plane? Because that's gonna make a big difference there. So
Energy are the same thing, then yes, it goes into describing the curvature of space. The two numbers don't match. However, we still haven't figured out how to quantize gravity.
okay. Actually, now I'm listening to that. That is true because the dark energy and the cosmological constant don't match. Because well, number one, you're talking about like an energy density. Okay, that's in the dimensions of energy divided by a volume. Because oh, sorry. Thank you, Astronomy Cast. Great for this different stuff and things about the universe and cosmos. And I think I need to sign up for Fraser's Patreon. This is not an advertisement, but I feel like I've learned so much from what he put out. So you try to help people where you can. Welcome, Kali. Kali, I think many people would agree with you. It does seem to really help with acceleration. Well, because gravity is basically the three-dimensional acceleration. Because well, it's yes. Yes, because it's a distance. So it's a length, it's a cubic length divided by time squared. Okay. So length divided by time squared is acceleration. Okay, so you get like meters divided by seconds squared. Yeah, yeah. That just means you're accelerating. You're going faster. It's like you're driving in your car. Yes, yes. And on the East Coast and Greater Massachusetts, we call our motor vehicles cars. All right. So you hop in your car. You need to get on the highway. Well, if you're just putzing along, or you had a geometro like I did at one point, you seem like a constant struggle for survival. So you gotta accelerate. And what happens when you accelerate? You get pushed back. Why? Because you're continuing to go faster and faster. So that's an acceleration. That's something as human beings that happen to be blessed with enough senses and the ability to comprehend this stuff. All right, we can understand that. And you can have a little acceleration and go, or you can be going really fast and you're pinned back. Okay. But that's something we can at least kind of relate to. Okay. Forgot what the heck I was. Oh, acceleration. Thank you, Kali. Uh, but okay, we're gonna break down this stuff. Don't worry. Nope. I don't expect anybody to know what this means because I don't know what this means. I just know it happened to hit the numbers really, really quite well, and it seems to be algebraically fairly pretty. So we're gonna get into this whole thing. Okay. So we went through a little clip, and Dr. Gay was sharing that basically dark energy, as we know it, that's in the dimension of energy divided by volume. So energy divided by a length cubed. Okay, it's okay. I'm saying these words, but let's actually break it out. So all right, let's go over here and share with the class. All right, okay. So yeah, given the power of Wolfram Alpha, aka it allows a monkey like me to use it like a magic typewriter. So I'm like, all right, so we're talking about dark energy. Let's see what that is. Okay. So it's not quantified as a unit, but we have the vacuum because energy density. Oh, hold on, I spelled that wrong, and I think we need to put it density. And we need to put it, okay, so vacuum energy density, like we were saying. Basically, J, that's just a joule. That's just the unit of energy. It's the reference one, like the meter. Probably some caveats there, but essentially, zeroth level approximation, it's the reference one of energy divided by cubic meters. So that gives us energy density. Okay. So okay, and the reason it has these units because you're doing a cubic volume, so energy is mass times the speed of light squared, E equals mc squared. Okay. So if you do that, that breaks up c squared is basically a length squared divided by time squared, because c is speed. It's just length divided by time. If you're going 60 miles per hour, 100 kilometers per hour, that is your speed. Okay. Now, so we've got a mass here, and then we have c squared, but we're dividing it by a volume. What the heck does that mean? That means normally, if we just take mass, this would be length squared, but we're dividing it by meters, which is to the third power. So that gets rid of those two powers and turns that into a minus one. It confused the heck. I'm like, how does this work? And then I'm like, oh, wait, math. You just need to keep track of just the powers and stuff like that. The only reason I'm able to do it is kind of like blocks. I'm like, all right, I can see this, I can see that relationship. Okay, I can subtract 3. If this was a 2 up here and I subtracted 3, I can get a -1. Okay, I can start to graph that. That's how. Yes, force equals mass times acceleration, and yeah, and then you can basically get most, or at least many, other physical attributes. I'm not going to make the full claim that you can get everything, but more or less. Opinion. Okay. So now we've got some dimensional stuff. All right. So let's actually get into it. Now we're looking for, now again, there are no numbers here. You just have these dimensions. Okay. Pardon. H2O. Sometimes you just got to hold some water. All right. So we're looking for our measurements. So what we're looking for is the universe vacuum energy density. Okay. So you get this whole thing here, and it's like, what the heck is this thing? Don't worry. It's like you see 4. I don't know. We got to worry about stuff blowing up with some Greek letter that terrifies everybody. And we got 8 pi. That's like 2 spheres. And then big G, the Newtonian gravitational constant. What's going on, Bone? How we doing? Oh, you look so adorable. Okay. I apologize. I was creeping on your puppy pic. All right. So what the heck is this? Okay. This is called Rho-vac, because that funky looking P is actually another Greek letter. They call it Rho, Rhoy, because they can. But basically, it's the unit of density. Okay. So what the heck is all this? Okay. So all you need to know is that this is why, at least the concept of being able to computationally reduce or look at something in a different way can make things a lot easier to try to figure out. Now, I'm not saying I know what this stuff means. I'm just looking at ways to potentially simplify and using measurements, Wolfram Alpha's database, as well as NIST code edit, basically as boundaries for a data set that I'm looking through and just looking for a way that at least I can think of it better. If it helps someone else, by all means. All right, so we've got those units. So the value for all this stuff, like 5 times 10 to the minus, very small number, very small amount, but it's not 0. Because remember, we're talking about the vacuum, quote unquote. What's a vacuum supposed to mean? It means there's not supposed to be any stuff in it. But apparently, according to our best measurements, there seems to be some stuff doing some things in the vacuum. What is it? Quantum fluctuations, aka maybe some hand waving. Maybe it's almost like there seems to be some force flowing throughout all things within our realm of persistence or universe. Sounds kind of like Star Wars. Now, again, personally, I preferred it. I have gotten to be a little bit of a Trekkie myself, but it's okay. It's okay. Yes. Row. Oh my God, that's a good adage. I think I'm going to totally steal that. Row your boat. To be fair, it's often, or at least the way I hear it is when people talk about the dark energy and stuff like that, it's like, it's what's that? What's the stuff that's driving everything apart? It's what's causing the universe to, according to our observations, be expanding. So yeah, it literally is rowing our boat. 3 rows, 3-dimensional space. That makes a lot of sense. I like it. It's that's very interesting. That is very interesting. Honestly, if I complete first year physics, I could probably actually give you an answer to that. I full disclosure, I'm not a professionally trained physicist. I do not have a PhD. I am not a mathematician. I am a dude on the internet that happened to have a lot of interest in science stuff and has consumed far too many YouTube videos, lectures, podcasts, this, that, and spent X number of hundreds, thousands or so hours on Wolfram Alpha using it like a video game. And rather than getting a new game being like, all right, quarter circle, high punch, Hadouken, it's like, let me type in these words, let me type in these words, because since it's natural language, I don't need to know all the jargon and stuff. I see some words, I look at a paper, they see these words, I look at these terms, even if I don't know what the terms, I can reverse image search the terms. You plug something into an LLM, at least now, more recently, you can kind of at least give you a kind of a summary that's more of a recent thing. The temperature, well, see, that is a good, see, when you take something like the cosmic microwave background, because that's about 2 point, was it 2.7, 25, 2.725 Kelvin, approximately. So you put that up, that doesn't include all the vacuum energy density there. Yeah. Oh, excuse me, 2.75, and then I think it's like 25 or something. I think it's, hold on. Cosmic background radiation. It's about, I know it's just above Euler's number. Euler's. Why am I, why is it not? Okay, 2.72548 with, okay. All right, so like 2.7 degrees Kelvin. Uh, Basically, that's not enough to make up for all the vacuum energy. And then, apparently, according to, if you ever heard of the Casimir effect, you're like, oh, what the heck is that? So that's supposed to be, you get like 2 plates. You bring them really close together, and then at some point it just splurch together apparently. And to my knowledge, that is interpreted as the Casimir effect, aka if you're basically at some point the wavelengths of all the vacuum energy fluctuations are going to push those together. Is that exactly what's going on? That seems to be the current interpretation. I mean, just the thought in my back of my mind is like, are are we sure it's not a gravitational effect? Because you're kind of bringing stuff together and everything. So I mean, I'm going to assume that the generalized interpretation that a lot of folks have gone through and, of course, have been replicated and everything is correct. I'm like, all right, that's cool. I'm totally for that. Uh, well, isn't temperature, Kylie's asking, isn't temperature only interactions per brevity, condensed matter particles? I think the generalized zeroth or thirst level approximation to temperature is it's basically a measure of the activity within some volume there. Like there's some stuff going on there. Um, to me, it's like, all right, if you're doing action and you're causing things to go into another LNG state, whether you're grinding something, you're gonna have heat. Heat was what? That's definitely the infrared spectrum. What is it? It's light. It's emitting light. So basically, the energy emission, as far as I know, is just to help keep everything in balance. Uh I mean, it is a good question. I mean, those are something I would submit to Wolfram's live stream because he actually worked as a professional physicist. So as a frequency given temperature for temperature. See, these are very interesting questions. And also, if you employ Boltzmann's constant, you can literally take mass, go through energy, and go through this, and you're going to get a magnitude. Because okay, let's just do this real quick. Well, This will probably actually even help me, just because. All right, so let's take something because I'm just going to take the units that I know. Planck mass. All right, I think I divide it by Boltzmann's constant, either that or multiply. Let's constant. Boom. I type the words. I do the little slash division sign. This is the reason I'm able to use this, because it's basically like an iPhone for like science noobs, at least like me. Okay, so that was not what it was. I think we gotta take that and divide. Hold on, what is Boltzmann's constant again? Where is its mass? This mass in the denominator or numerator? Numerator. Blah. It's the dimensions. Okay, so this is going to give us. Okay, no, I multiply. Okay, noob. Use it as a unit. Let's see. Okay, I might just be full of crap then. Or do I need to go to energy first? Is that what it is? It's the energy conversion. Okay, never mind. I lied. It's going to be c squared. And then I think we're going to have to divide. There we go. All right. Okay, I apologize. It's the energy conversion to temperature. See? Somebody that hasn't actually, I've actually never finished a full physics class. Like I've taken like astronomy, exploring the universe, both in high school and even when I took modern physics for like a week and a half my senior year. I never finished either class. There are differing reasons. But let's see. Nullius was commenting. CMB is just Planck's black body radiation. I would argue photon density defined vacuum energy, other properties being permittivity and permeability. Well, I mean, yeah. Well, I mean, permittivity and permeability, that's like E naught and M naught, or mu naught. It's basically the electric constant and the magnetic constant. And then if you do 1 over the square root of those, you're going to get the speed of light. I think those words were correct. Hold on. 1 over, don't need that there. Square root, magnetic constant, electric constant. Okay, that looks like the speed of light. All right, see. All right. Oh, see. I made it funny. Okay. And then just to break it up, hold on, let's go to magnetic constant. Interpretations, magnetic permeability, and then, or that's at least for, okay. This is basically for the electromagnetic field, because this is permittivity. All right, permittivity, and then permeability. Okay. So, cool. All right. I totally forgot where we were, so let's just go back to the other thing here. All right, so let's stop this. Okay. Okay, I put some stuff on the board. I got some. I'm going to leave these units here just because, well, one, you can actually see them. And one of the biggest things for me when I started going through all this, you see all this stuff, you're like, whoa, this is pretty, this is cool. I have no idea what the things on the things mean. It's, hold on, I need one more tangent. Hold on, we're gonna reference video we made. It's okay, it includes Richard Feynman. So, and let me see. Richard Feynman's most fantastic moment. Okay, this is from his time at Los Alamos. Let's bring it up.
How do you look at a plant that ain't built yet? I don't know. So I go in.
So this is a story from Los Alamos, and then he starts basically he was brought on. He didn't even finish like his degree and stuff, but basically he was a young, brilliant physicist. So Oppenheimer basically put him in charge of going over to where is it? Basically, he needed to make sure the plant was all right, because otherwise, you store too much radioactive material together without shielding and stuff might be a bad day. And a lot of that stuff wasn't really known, may or may not have been secret at the time. So we'll continue.
Went to this room with these fellas, take me into the room. There was always a Lieutenant Zumwalt that was always coming around with me, taking care of me. You know, I had to have an escort everywhere. So he goes with me, takes me into this room, and there are these two engineers and a long table, great big long table, tremendously covered with a blueprint that's as big as a table. Not one blueprint, but a stack of blueprints.
Oh, okay. Now, again, you're a physicist. You're a young person. You haven't even gone through everything to get your PhD and everything. You're here. You see this giant table with all these blueprints on it. All right. You're in charge of keeping this place safe. What happened at this time, a Richard Feynman, not professor.
I took mechanical drawing when I was in school, but I wasn't too good at reading blueprints. So they start to explain it to me because they thought I was a genius. And they start out, Mr. Private, we'd like you to understand, the plant is so designed. You see, one of the things we had to avoid was accumulation. Problems like there's an evaporator working, which is trying to accumulate stuff. If the valve gets stuck or something like that and accumulate too much stuff, it'll explode.
I mean, these seem like very reasonable things. You're going through, you're explaining these things. It's like, all right, you happen to be there. It's like you're following. Maybe you're not a really good understander of blueprints, but you're at least following along with the logic. And then, if a whole bunch of people think that you happen to be wicked smart, as we'd say on the East Coast, or a quote unquote genius, some folks might think that this person is absorbing every word I say. Now, again, Professor Feynman happens to be a Nobel laureate and stuff. A lot of people like him. A lot of people have learned science from him. This was his experience when he was getting explained the engineering aspect.
So they explained to me that this plan is designed so that no one valve, if any one valve gets stuck, nothing will happen. It needs at least two valves everywhere. So then he's explaining how it works. The carbon tetrachloride comes in here, the uranium nitrate from here comes in here, goes up and down, it goes through the floor, comes up through the pipes, coming up from the second floor, through the blueprints, down, up, down, up. Very fast talking, explaining it. Very complicated chemical plant. I'm completely dazed. Worse, I don't know what the symbols on the blueprint mean. There's some kind of a thing that at first I think it's a window. It's a square with a little cross in the middle like this, all over the damn place. Lines with this damn square, lines with this damn square. I think it's a window. No, it can't be a window because it ain't always at the edge.
Okay. I'm just saying, one of the scientists that a lot of folks will raise up and be like, this is one of my favorite scientists of the past. Richard Feynman, he was working on the Los Alamos project. Had no idea what the symbols and the blueprints meant. Things ended up working out, and we're going to show why, because occasionally some people have said it's better to be lucky than good. We continue.
I want to ask him what it is. Now, you must have been in a situation like this. You didn't ask him right away. Right away, it would have been okay. But they've been talking a little bit too long. You hesitated too long. If you ask them now, they'll say, what are you wasting my time all this time for? I don't know what to do. I think to myself, I swear, I'm often in my life I've been lucky. You are not going to believe this story, but I swear it's absolutely true. It's such sensational luck.
So, I mean, I did use that for, what was it? Shout out to Kurt Mungle's Theories of Everything. When I did the How I Stumbled Upon the Best Theory of Everything in quotes there, I used that quote. Why? Because it's like, I mean, you just got to listen to it. I'm sorry. It's like, often in my life, I've been lucky. You are not going to believe this story. It's so fantastical.
Dude, I think to myself, I swear, I'm often in my life, I've been lucky. You are not going to believe this story, but I swear it's absolutely true. It's such sensational luck. What am I going to do? What am I going to do? I got an idea. Maybe it's a valve. So in order to find out whether it's a valve or not, I take my finger and I put it down in the middle of one of the blueprints on page number 3 down in the end. I say, what happens if this valve gets stuck? Figuring they're going to say, that's not a valve, so that's a window. So one looks at the other and says, well, if that valve gets stuck, and they go up and down in the blueprint, up and down the blueprint, other guy up and down the blueprint, back and forth, back and forth, back and forth. They both look at each other and they chick, 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 and they turn around to me and they open them out like this. You're absolutely right, sir.
So, by sheer luck, asking if, what if this valve gets stuck? Not knowing if it's a valve or a window. Apparently, that helps save the plant or do something very useful. And then of course Lieutenant Zumloff has to ask the question.
So they roll up the blueprint to the way they went, and we walked out. And Mr. Zumloff, who'd been following me all the way through, he says, "You're a genius." He said, "I got the idea you're a genius when you went through the plant once and you could tell them about evaporator C21 and build 9207 the next morning." He says, "And when you knew all about the neutron energy, but when you have just done," he said, "was so fantastic. I want to know how. How do you do something like that?" I told him, "You try to find out whether it's a valve or not."
Yes. So I'm just saying, occasionally there are people that are quite revered by some. I'm not saying that's a good thing or a bad thing, that happen to occasionally not know what the symbols mean. It's okay. Well, that's what learning is for. Why? Because we want to do a bit better. All right, so let's actually get into this whole dang thing. Let's actually, since we're over half through the show, let's actually get into what the heck we're talking about. All right, so what we're going to do is we're going to, where's the eraser? All right, we're going to erase this guy. I'm going to leave these units just for reference because this is really, aside from the little pi symbol and just some numbers, an 8, a 3, a 2 or something. Yes. Oh, yeah, 2, 3, and an 8. Okay, that's all we really need. All right, so I'm going to go through this. I'm going to show at least my whole dang thought process, how just a random simian like me, a magical computer book, shout out to Inspector Gadget, and some crazy computational video game that is Wolfram Alpha had us go through this. All right. So first, all right, let's get this up here. Make sure everybody can see. All right. So what we're gonna do is, all right, all right. So this thing, EP equals Planck energy. What is that? That is the maximum energy, or at least the ability to express a maximum energy. FP, that's the Planck force. That is the maximum force. Some people would argue about these. Some people would argue about these, but I believe per unit volume, is that the way to say that? Per unit something, these are the max. Because basically, if you cram the Planck energy into the Planck volume, you're basically going to get a black hole. So at least as far as we know. So you can't really do much more. You're kind of limited. All right. So at least for this, EP is the Planck energy, the maximum expression of energy. The Planck force, FP, is the maximum expression of force. M is meters, because we're using the SI system and stuff, so that's what works. And then big J, that's just joules. That's just the reference of energy. It is the reference of 1 for energy, while M is the reference of 1 for length. Okay. So all we got to know is, all right. So let's take a look at the problem. What the heck is the problem? Well, the problem is, let me close that out. All right. So let's look at some stuff. All right. Hey, welcome, Rick. How you doing, my friend? Good to see you. Good to see you. Hope unwinding reality is going well. All right. Inspector Gadget. Boo. Oh my God, Sandra, I totally got that right away. Yeah, okay. Yeah, that sounds right. Okay, yeah. So it's the maximum per Planck mode. You go there, you're not going to shove anymore. And it's going on. All right. Cool. All right. So let's, where was I? Sorry. I got distracted by knowledge and occasional old memes. That's never happened before. All right. So first thing, the vacuum energy. All right. So we got to go back to, I think we had it here. Hold on. I was sorry, Rick. I was getting confused about. I was trying to convert mass with temperature without doing the energy conversion. That was a mess. Okay, what a noob. All right, so we got this universe vacuum energy density. So we got all this. Oh my God, that's a lot to deal with. Okay, number one, what is this? C4 and then big G. All right. So what happens if we do this? Well, literally just type in what exactly is there, divide by big G. Okay. Now we need to be specific because it's Wolfram alpha. We want the units. Okay. So you get this. That's a ginormous number. And what's oh look, it equals the Planck force. So that means this whole dang thing here, this and this, we can just literally separate out as the Planck force. Okay, my mind is clicking because I'm realizing right now I've missed something completely obvious that's been in front of me the whole time. I don't know exactly what it is yet, but it's coming to me because this was not the direction I wanted. Okay. And then this lambda was that lambda that we had up there, and then this 8 pi. Don't blame me, blame Einstein if you want, because the whole the inverse of the Planck force. It's 8 pi divided by. Let's see. Should be it's 8 pi. Protective brackets just because units. I should have just done Planck force. Okay, yeah. So one kappa on the Einsteinian constant. This basically it's the Einstein gravitational constant. So basically the C4 convention. What do you got there? It's basically 8 pi divided by the Planck force. Cool. Let's see. Oh yeah. Yeah, Rick's Einstein. I'm misspelling Einstein, aren't I? Oh my God. There we go. It's not like I've been here a couple of times. Yeah, because this is one of the few places you see it. Yeah. So kappa, basically it's 8 pi, the Newtonian gravitational constant divided by C4. So basically it's 8 pi divided by the Planck force. Okay. So that's something I can at least kind of put into a section somewhere in my mind. I'm like, okay. All right. So let's go back over here. Okay. I think I'm going to deviate because otherwise I'm going to really confuse myself. Okay. My thought process, well, at least the vacuum energy or whatever it is, I look at this, I'm like, dang, that's a really small number. So I'm like, all right, let's click on this number. And to be fair, even that it's a little bit off the universe vacuum. And to be fair, we only really notice so many digits. All right. So I look at this. One of the things I've learned from Rick Thad and John Williamson is, all right, what if I looked at it another way? 2 times 10 to the 9, blah, blah, blah. It's swapping the dimensions around. I'm like, okay. To be fair, that's not how we got there. I just happened to notice because when I actually went to look at this, I'm like, that number looks a little familiar, or at least the number and around that number in magnitude. I don't remember the dimensions. So I'm like, huh. So what if we looked at something like, I don't know, the Planck energy? Oh, I mean that's a pretty big number. It's within joules and stuff. All right, cool. What if we took the inverse? Huh. 5 times 10 to the minus 10. Wait a second. That number looks a little familiar. It's in the wrong dimensions, but wait a second. So rho lambda, the universe vacuum energy density, 5 times 10 to the negative 10. Universal Planck energy, 5 times 10 to the negative 10. Now it's in inverse energy, so I mean, that doesn't really do me any good. But I'm like, okay, that's an interesting thing. And you look around, and you're like, that's an interesting coincidence. And then you go through and you're trying to know all these things. It's like, all right, what if I literally just did the naive thing? What if we literally just been like, all right, what if, because if we were to divide it by joules, or 1 joule, we're gonna get a dimensionless number. All right. So the thought is, that if I do the goofy thing to get the right answer, joule squared. Oh, look, this is giving us energy. I mean, it's not the correct energy that we're looking for, but it's at least in the right dimensions now. And for a while, I'm like, all right, that's a neat little trick. How the heck can I justify that? I'm like, now the interesting thing is, if we take that looking at things inversely, and we have Rick in the chat, so we'll just do this little thing, because well, if you learn something, you give credit where credit's due. If you have something like, let's say, the speed of light squared, c squared, okay. I guess it's a really big number. Okay. That's cool. All right. Who cares? It's that thingy we use in an equation, assuming it's under, it's not moving or rest mass. Okay. Well, let's do the same dang thing we did. Let's do 1 over that. Okay. 1 over the speed of light squared. Okay. It gives us this really small number, that 1.113 times 10 to the minus 17. And I get second squared divided by, okay, cool. We've got a really small number. What if we did something similar to what we just did over there? Let's do the silly thing. Let's divide 1 joule by the speed of light squared. Oh, that's interesting. Wait a second. 1.113 times 10 to the minus 17 kilograms. That's, oh, it's the relativistic mass of 1 joule. Wait, wasn't that number? Oh, why is it giving us the same magnitude of 1? Because within our coherent system of units, our reference 1 of energy is the joule. Fancy that. But if that's true, that might mean that joule squared, if that's a reference energy for c squared and we squared again, that would be like something to do maybe with the speed of light to the 4th. Wait a second, didn't we just see something like that like a minute or so ago? Oh, very interesting. All right, so let's take a quick break. So, all right, the thought process was, it's like, all right, we got something. Let's do that Planck energy. So we'll just do our little shorthand over here. So we're gonna do, all right, gonna do E P, big number. All right, what do we do? Are we dividing it into J, big J for joules, our reference 1 of energy squared, and then that gives us an energy, or at least within the magnitude of the vacuum energy density. Okay. Again, full disclosure, when we actually go over there, it's literally just giving us energy. It's not energy density, because to do energy density, that's going to be a cubic volume. Okay. What if we did the very naive thing, just to make it work, and we did, I don't know, meters cubed, because that's a volume. All right, it's about 96% the universe vacuum energy density. That's neat. This seems very contrived and everything, but we've literally only got ones in here, or at least ones of something. We've got the reference one of energy, joules. Oh, let me go back because we got to add this here. We got to add our M. Why? Oh, he doesn't like some M&Ms. Okay. So our contrived method to get to the magnitude and perhaps even attempt to interpret the vacuum energy density. We've got the reference one of energy, the joule squared. We've got the reference one for the maximum energy, the Planck energy, and then we have the reference one of length, the meter cubed for a volume. Okay, and then we get pretty close to the vacuum energy density, but if, and again, this depends upon interpretation, as Dr. Gay had said earlier, that if one assumes that the dark energy, the vacuum energy, basically is or is at least some form of a component of the cosmological constant, or if we make that assumption, because again, the numbers are different, they're different dimensions, because one's the energy within a volume, and then the other is expressed as an inverse length for whatever reason. Because things both be going away. Okay. So if we were to assume that, let's pull out our spherical cows and be like, all right, if we assume that that's something to do with curvature, how might we figure that? Or how would we factor that into something that's just got some dimensional stuff? Well, there is something that relates to curvature that a lot of folks know. It also happens to be a very tasty snack. Our friend pi. Okay, that's cool. That's not correct, though, because it's going to throw our number off. We need something else. Perhaps something that maybe we could intuit and hopefully it would help give us at least approximately a right answer, or at least an answer we could provide an argument for. Well, if we're talking about energy density, dimensity, yes, if we're talking about energy density, that's energy contained with a volume. We seem to live in three spatial dimensions. So, three. You could also break this apart. You can just have your dimensional stuff over here. And you have your geometric thing over here. Cool. What happens? What happens if we were to make that crazy assumption? I don't know. Let's find out. Probably actually share, be like, oh, you're hiding stuff. Of course. All right. So I got pi, the curvature constant, at least for circles. Divide by 3. Is that our 3 spatial dimensions? I don't know. Divided by joule, the reference one of energy squared, divided by the reference one of length cubed for a volume, and the maximum one of energy. Gives us this number here, this 5, yada, yada, times 10 to the minus 10 joules per cubic meter. And that's approximately the vacuum energy density. Cool. Let's see. It would be I'm trying to figure out what the QP is, Sandro. See, he's mentioned this time. I don't know what Q is. Oh, Planck charge? Oh, QP? Oh, that would be Planck charge. Slow on the Planck chart. Oh, wait a second. Let's see what happens. It gives us that big number. I mean, to be fair, I mean, there are ways to convert from like the Planck charge and Planck temperature into like the Planck energy. So that's why you have Boltzmann's constant and Coulomb's constant. I believe that's correct. All right. Now let's see. I mean, you can throw in the Planck temperature, but then you need to adjust that with Boltzmann's constant. I mean, I could throw in the Planck mass and do c squared there. This is just the kind of the most condensed way I've been able to find it, because before this was actually just set to. I originally had this set to like 1 joule, and just because of a random calculation that said it's like, oh, it looks like it was within 2 pi of the relativistic mass of 1 joule or whatever I had. Let me I think I remember what it is. Let's go over here. So let's do I think I had it as joule equals square root, or the geometric mean of the Planck energy, and then we solve for x joules, and then this was divide by, I think, pi divide by 3. I think that's right. Might have it backwards. Okay. Yeah, so it gives us the same number there, and we were solving for joule. Yeah, so basically I just had this set up before, basically just calculate for the reference one of energy. If you set it up this way, you take the square root, aka the geometric mean. The geometric mean just means you have 2 numbers, or you have x number of numbers. If you have 3 numbers, you just take the cube root. If you have 4 numbers, you take the 4th root, yada yada. So basically, this is the geometric mean of that with this factor in here, that pi divided by 3. And then I'll give you that number. And since we're solving for x, which was in joules, that would be in joules. So trust but verify, we click joules. And then you could add in meters and stuff like that if you want. It's so yeah. So if you were to add in the meters, and it actually comes out the same way, except you're adding those dimensions after the fact and everything. So yeah, so basically approximately the universe vacuum energy density there. Okay. So this was quite fun. I see this and it's like, okay. Yeah, I mean, that's kind of cool. So at least at this point. So now what the heck does it mean? Oh God, I realize I'm almost out of time now. All right, so we're not actually going to do the cosmological constant. I apologize, bait and switch, folks. But for the vacuum energy density, or we're going to claim this is equal to our rho lambda there, or our vacuum energy density. Okay. So let's just break this down. What do we got? We got the reference one of energy squared divided by the maximum and one of energy times the reference one of length cubed. All right, so we got energy squared, basically the ratio between our reference, which joule, which apparently is based upon c squared. We got the Planck energy, and we literally just got meters cubed. I think. And again, a lot of times you'll hear about, oh, the vacuum energy, oh, it was 122 orders of magnitude or something. I'm like, you throw the Planck length in instead of meters. I think this is about 114 orders of magnitude off here. So I'm like, I can see how that could happen. Now, again, more justification is going to be required, but I'm like, if we were to interpret this as some form of curvature, we've got this dimensional combination of ones, whether it's a reference one like this or that, or a maximum one of energy. And then we've got a factor of pi, circular curvature constant, divide by 3. I mean, it also happens to be 60 degrees, if you want to interpret like that. But that seems to imply at least maybe some curvature-ness. Divide by 3. What might that mean? guess we're just gonna have to wait and find out and see where the experiments take us. So I think it's about where we're at right now. All right, I see some folks got some other stuff going on. The energy is on a function. Nellius is commenting, function of temperature. Okay, so if we do, hold on, let me bring one last thing up. Just because I don't know this stuff well enough, so I should probably actually practice. All right. So if we did something like the Planck temp, very large number, 10 to the 32 Kelvin. All right. We summon the Boltzmann's constant. So it basically brings us to the Planck energy. So that's the Boltzmann's constant is the bridge between this. That's why, as long as you have energy, you could approximate an effective temperature. And I'm like, all right, well, if energy is photons and temperatures are expression of photons, it's like, I don't think, I could be completely wrong, but I think there's very interesting avenues, and I don't think there's necessarily one right way to try to parse reality. Why? Because apparently there's a lot of really smart folks out there that are coming from all these different ways, and I don't think you see so much stuff that just happens to be a coincidence without it actually maybe telling us something. Now, again, it could be complete bunk, but we'll see. Also, one of the very interesting things I heard earlier, I'm sorry, this is a bit of physics gossip, but I was re-listening. Apparently, it came up in my playlist. One of Professor Sean Carroll's biggest ideas in the universe things. At one point, he was talking about, he's like, oh, we got Planck's constant. We call this H bar. It's the reduced constant and stuff. He's like, I have no idea what the number is. Why? Because all good physicists write this as one. And at that point, I realized I am not a good physicist. If I could even attempt to, somebody called me like a mathematical physicist on paradigm drift. I'm like, oh, that was a very great honor. I mean, it's totally untrue, but I don't know. It's because it's one of those things. If you're a good physicist and you're doing it that way, great. But might there be something we're missing if you just set it all to one? And again, take it for what it's worth, but at least according to Wikipedia and stuff, one must be careful because a lot of these constants that we have, depending on which one you take, are you assuming they're all one? Because if we only have measurements and basically if we only have measurements of big G to like 5 significant digits, of accuracy to our knowledge, then I don't know. Speed of light, we got to like 9. H bar, we got to 10. It used to be 12, but there was very large error in the last two. Um, it's very interesting. It was at that point I realized, oh, that means a lot of folks might not be looking or at like something like 1.05 times 10 to the minus 34 and be like, oh, that's obviously the magnitude of H bar. Because I am a bad physicist. Uh, numerological physicist. There we go. I like that because that's my friends. I'm gonna stand by. Okay, we don't need that anymore. All right. Numerology is numerology until it explains more with less. Does this explain more with less? I don't know. It's it's just a way to computationally reduce things. Unfortunately, we're gonna have to wait till tomorrow until I can actually go back to what I meant to do last week and actually go through and at least provide my base level interpretation about what might be going on. And what we're going to do is we're going to truncate it a little bit at certain pieces. Because I'm going to be like, all right, we're going to start off with I'm going to look at a thing, I'm going to conjecture, and we're going to be lined up with a lot of things. And we're going to start to deviate. And we're going to start to deviate more from what a lot of other people say. And then we're just going to go completely off the farm as I conjecture wildly. Now, hopefully, any of y'all who are watching now or temporarily in the future can let me know how far off my rocker I am. Or maybe give me some breadcrumbs to go in a different direction. But that's all we got for right now. So that's been fun. Take care of yourselves, everybody. Peace out. It's a crazy word out there, but I think 2025 is gonna be a heck of a year to be alive. So peace out, everybody.